Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 17. In this session, the EMF equation, voltage current relations, power stages. These are the topic discussed. And a few examples are also worked out in this session. So let's start with the EMF equation. Before that, let's assume that the flux per pole is equal to phi and P the number of poles, Z is the total number of armature conductors, N is the speed of the generator in RPM. RPM is revolution per minute, and A is the number of parallel paths. Flux per pole, that is the magnetic flux coming out of one pole. Let it be equal to 5 Weber. P is the number of poles of the machine, 2 pole, 4 pole, 6 pole, etc. Z is the total number of armature conductors. And N is the speed in RPM. RPM is revolution per minute. And A is the number of parallel paths. Parallel path means the conductors which are connected in series coming across the armature terminals. And we know that the relation for a lap-wound machine, number of parallel paths is equal to number of poles, and for a wave-wound machine, number of parallel paths is equal to 2. Now the average EMF induced in a conductor is the flux cut by a conductor in one revolution divided by time for one revolution. Let's assume a 4-pole machine. The poles are north, south, like that it is arranged. One conductor. So flux by a cut by a conductor in one revolution is, in one revolution, the conductor is moving under the influence of 4 poles and the flux per pole is 5. So in one revolution of the conductor, the flux cut by it is equal to 5 into P. Flux per pole into number of poles. In this case, it is 5 into 4. There are 4 poles. Divided by time for one revolution. The generator is rotating at the speed of n RPM. That is n revolution in 1 minute, or n revolution in 60 seconds, and the time for one revolution is equal to 60 by n seconds. So it is rotating at a speed of n RPM, n revolution per minute. So it's completing n revolutions in 60 seconds. So it takes 60 by n seconds to complete, or time required for one revolution is 60 by n seconds. N revolution in 60 seconds. So one revolution it will complete in 60 by n seconds. So substituting here, the average EMF induced in a single conductor is 5p divided by 60 by n, or 5pn by 60. Now the EMF induced across the armature terminals, or EMF available across the armature terminals, is equal to average EMF in a conductor into number of conductors per parallel path. Parallel path means the conductors connected in series coming across the positive and negative terminals of the armature. So average EMF in a conductor is 5pn by 60. Conductors per parallel path is Z by A. So multiplying will get EMF induced is equal to 5ZnP divided by 60A. Phi is the flux per pole, Z is the total number of conductors, N speed in revolution per minute, P is equal to number of poles divided by 60A. A is the number of parallel paths. And we have to remember this relation also. A is equal to P for lap wound machine, and A is equal to 2 for wave wound machine. So from this equation, E is equal to 5Z then P divided by 60A. In this, for a particular machine, the number of armature conductors, number of poles, number of parallel paths, all these parameters are constant. So the only variables are phi and n, that is flux per pole and speed of the generator in RPM. So phi and n are the parameters which are changing. So we can generalize it as E is proportional to phi into n. Or from that we can reduce this relationship. E1 by E2 is equal to phi1 n1 divided by phi2 n2. So this is also an important relation. Now next is current relation. Now IA is the total current supplied by the generator or armature, out of which a portion goes to the field winding. A and AA are the terminals of the armature, and F and FF are the field winding terminals. So out of the current supplied, a portion goes to the field winding, remaining is delivered to the load. So from this diagram it is clear that total current supplied by the armature, that is IA, is equal to load current plus field current. So armature current is equal to load current plus field current. Next is the voltage relation. Let V be the terminal voltage, that is voltage across the load terminals. I is the load current. IF is the field current. IA is the armature current. E is the induced EMF. So the armature, you can represent it like this. A constant voltage source in series with a resistance. So IF is the field current. I is the load current. And the voltage across the load terminals is equal to V. So E is equal to, from this diagram it is clear that V is equal to E minus IARA. So the complete armature current flows through the armature resistance. There is a voltage drop across it which is equal to IA into RA. So terminal voltage is equal to E minus IARA, or induced EMF E is equal to terminal voltage plus voltage drop in the armature resistance. Sometimes in when we are working out examples, the voltage drop across the brushes are also to be considered. There will be a small voltage drop across the brush. It is given, then E is equal to V plus IARA plus voltage drop across the brushes. Now next is power relation. So output of the generator is Vi. Field copper loss is V into IF. Let's take this figure itself. So output, what is the power delivered to the load? It is V into I. That is the output of the generator. V is the voltage across the load and I is the current taken by the load. So product will give you the power consumed by the load. Then what is the power dissipated as heat in field winding? P into IF. V into IF is the field copper loss. Then what is the armature copper loss? The current flowing through the armature resistance is IA. So the armature copper loss is equal to IA square into RA. I square R loss. What is the power developed by the electrical power developed by the armature? E into IA. Magnitude of this induced EMF is E. Current delivered is IA. So power developed by the armature is E into IA. So the total power developed is equal to E into IA. It's equal to output plus field copper loss plus armature copper loss. So out of the total power developed, a portion is dissipated as heat in the armature conductors, that is IA square RA. Another portion is dissipated as heat in the field winding, which is equal to V into IF. And the remaining is supplied to the load, that is V into I. So the total power developed by the armature E into IA is equal to output plus field copper loss plus armature copper loss. So this we can prove from this relation also. That is, we know the equation E is equal to V plus IARA. We multiply this equation throughout by IA, we'll get E into IA is equal to V into IA plus IA square R. Now, another relation is that IA is equal to I plus IF. So substitute for IA in this equation as I plus IF. Again, expand these terms. So that is E into IA is equal to VI plus V into IF plus IA square R. So the total power developed by the electrical power developed by the generator is equal to output plus copper losses. Copper losses are field copper loss and armature copper loss. Now the power stages, if you consider the input is mechanical. So input is supplied by the prime mover. Prime mover means the machine which is driving the generator. It can be another electric motor or a diesel engine or something like that. So generator input is mechanical. It's converting mechanical energy to electrical energy. So from the input, a portion is lost as core losses and mechanical losses. Core loss and mechanical loss. Core loss means mainly in the armature. Armature is rotating in the magnetic field produced by the field poles. So definitely there will be hysteresis and eddy current losses in the body of the armature. That is the core losses. The armature is rotating under the in the field produced by the field poles or in the magnetic field produced by the field poles. So the armature is continuously moving. So there will be hysteresis and eddy current losses in the armature. Also there is core losses, that is hysteresis loss and eddy current loss. Hysteresis loss plus eddy current loss. Then mechanical losses, that is friction plus windage. Frictional losses, friction plus windage. Friction means there are two frictional losses in this case, that is bearing friction and brush friction. Bearing means our armature is mounted on ball bearings. This is armature shaft. Shaft is mounted on ball bearings on either side. So there will be a certain amount of frictional losses here. That is brush friction loss plus bearing friction plus brush friction. That is the carbon brushes are touching the commutator. It is exerting a certain amount of force on the commutator so that the connection is firm. There is a certain amount of frictional losses there. So frictional losses are bearing friction and brush friction plus windage losses. Windage loss means the armature is continuously rotating and due to the friction with the surrounding air, there will be some sort of resistance offered to the movement of the armature. That is windage loss due to wind or friction with air. So from input, these losses are met and the remaining only is the power developed, electrical power developed by the armature. So input is mechanical. From input, these losses are met, rotational losses. It's called rotational losses means when the armature is rotating, that time only these losses can happen. The armature is stationary, then hysteresis loss or eddy current loss will not take place. There will be no friction loss, no windage loss. So these losses can happen only when the armature is rotating. So it's called rotational losses. So rotational losses are core losses and mechanical losses. Core losses, you know it, that is hysteresis loss and eddy current loss happening in the armature because the armature is rotating in the magnetic field produced by the field poles. Core losses happening in the field poles can be neglected. Most of the cases it is neglected. Only very small amount of core losses is happening in the field poles, mainly in the armature. Then mechanical losses are friction and windage. These are the components of mechanical losses. Friction means bearing friction and brush friction. So bearing friction, the armature is mounted on bearings and the frictional losses happening there, that is bearing friction. Brush friction means the brushes are in firm contact with the commutator. So certain because with the springs, certain amount of force is exerted on the brushes so that the contact is firm. So the losses happening there, that is brush friction loss. Windage means when armature is moving, it is in constant friction with the surrounding air. So that is called the windage loss. These two are mechanical losses. So core loss plus mechanical losses together, it's called rotational losses. Rotational losses are happening only when the armature is rotating. So input minus rotational losses, the power developed, the electrical power developed by the generator, that is E into I, out of which copper losses are met, that is armature copper loss and field copper loss. These two copper losses are met, and the remaining is supplied to the load. This is the power supplied to the. So I'll summarize the total losses happening in the DC generator. We have seen these losses are copper losses, core losses, and mechanical losses. Copper losses are the armature copper loss, field copper loss, and I-square loss at the brush contact point on the commutator. Then core losses are hysteresis and eddy current losses, mechanical losses, brush friction, bearing friction, and windage. Then these put together, that is core losses or magnetic losses and mechanical losses put together, are called the rotational losses. So these are the total losses happening in the DC generator. The next is series generator. So in a series generator, the field is connected in series with the armature. So the armature, field, and load all are connected in series. That means the current through the armature, current through the field winding, and current through the load all same current. That is armature current, field current, load current, all are same in this case. And the generated voltage is equal to terminal voltage plus voltage drop in the armature resistance plus voltage drop in the field resistance. In certain cases, brush drop also can be added. Brush voltage drop. So the generated voltage is equal to terminal voltage plus voltage drop in the field winding resistance plus voltage drop in the armature resistance plus brush contact drop. So here the entire armature current is going through the field winding. So field winding will be having comparatively less number of turns. Comparing with a shunt generator, in a series generator, the field winding will be having less number of turns because the armature current, the entire armature current is passing through the field winding. So to produce a certain amount of MMF, MMF is the product of current and number of turns. Since current is high, number of turns will be less. And the field winding, field conductors or the coil should be having sufficient capacity to carry the large amount of current. Then applications, shunt generators are used for battery charging, street lighting, alternator field excitation, etc. Alternator field excitation means to excite the field winding of the alternator, a DC source is required, and quite often a DC generator is used for that purpose. Then series generator. Series generator is mainly used as a booster on DC feeders. Say this is DC mains, DC bus bar, positive and negative. The series generator is connected in series with the load. So these two terminals are going to the load. This is the series generator. So the entire load current passes through the armature as well as the field winding. Now, normal case, if this series generator is not there, under peak load condition, there will be voltage drop in the lines. So that is IARA drop. This is a DC circuit only. So resistive drop will be there in the transmission or distribution lines during peak hour. So here, since a series generator is coming here, so when load current increases, the field excitation of the DC series generator increases, and accordingly the terminal voltage increases. So the voltage generated by the series generator is in series with the system voltage. If this voltage is V and if this voltage generated by the series generator is V1, then this will be added. So the voltage drop that is happening during the peak hour period can be compensated by an additional voltage being generated by this series generator. That means whenever the load current increases, the field excitation increases proportionately and the generated voltage increases. So only thing is that it should be on the linear portion of the curve. That means after a certain stage, the field will reach saturation further. If the field current increases also, there won't be corresponding increase in the generated voltage. So the generator should operate during the linear, in the linear portion of the curve, voltage curve. Then let's work out certain examples. A 4-pole lap-wound DC shunt generator has 600 armature conductors, flux per pole of 25 milliweber and runs at 1000 rpm. Find EMF induced. So the values are given, this substitution only. Number of poles 4, it is given 4 pole. It's a lap-wound machine, so number of parallel paths is equal to number of poles is equal to 4. Flux per pole 0.025 Weber. Then speed is 1000 rpm. So E is equal to phi z n p divided by 60A, phi z n p divided by 60A. Substituting, the induced EMF is 250 volts. Next question. A 6-pole wave-wound shunt generator has 120 armature conductors and runs at 1000 rpm. If the flux per pole is 40 milliweber, find the EMF induced. This also just a substitution only. 6-pole, that is number of poles 6. Then wave-wound. Wave-wound means parallel paths is equal to 2. Number of armature conductors 120. Speed is 1000 rpm. And flux per pole 40 milliweber or 0.04 Weber. So substituting these values, phi z n p by 60A, phi z n p divided by 60A, the induced EMF is 240 volts. Next. A 4-pole wave-wound DC shunt generator having 160 armature conductors has an induced EMF of 240 volts and runs at 900 rpm. Find the flux per pole. If the flux is increased by 10%, find the new value of EMF induced. So 4-pole machine, number of poles is equal to 4. Wave-wound parallel paths 2. 160 armature conductors, Z is 160. Speed is 900 rpm. And induced EMF is 240 volts. We have to find the flux per pole. So 240 E is equal to phi Z 160 N P divided by 60. Solving, we will get flux per pole is equal to 50 milliweber. Then if the flux is increased by 10%, find the new value of EMF induced. So E is proportional to phi into N. So in this case, speed is constant, so E is proportional to phi. So let's assume a direct proportion. So if flux is increased by 10%, EMF also should increase by 10%. So that is the present voltage induced is 240 volts. 10% increase means 240 plus 10% of 240, that is 240 plus 24, 264 volts. Next. A 4-pole lap-wound DC shunt generator delivers 200 ampere at a terminal voltage of 250 volts. Field resistance 50 ohm and armature resistance 0.05 ohm. respectively. Neglect brush drop. Determine. These are the 5 parameters, 6 parameters to be determined. So number of poles is equal to 4. It is a lap-on machine, so number of parallel paths also is equal to 4. Then load current is equal to 200 ampere. It delivers 200 ampere. At a terminal voltage of 250 volts, that means load terminal voltage is 250. Field resistance 50 ohm, armature resistance 0.05 ohm. So first we have to find out the armature current. For that we have to find the field current first. So field current can be found. Here the voltage is available. Voltage across the armature terminals or field terminals is available. That is 250 volts. Field resistance is 50 ohm. So field current is equal to V divided by resistance of the field winding. So IF is equal to V divided by RF, that is 250 divided by 50, that is 5 ampere. So field current is 5 ampere. So armature current can be found out. Armature current is equal to I plus IF, that is 200 plus 5, 205 ampere. So IA is equal to I plus IF equal to 205 ampere. Next is current per parallel path. Here number of parallel paths is equal to 4. Therefore, current per parallel path is equal to 205. That is, the armature current is 205. It's equal to current per parallel path is equal to IA divided by A. That is, IA is 205 ampere. A 4 parallel paths. That is 5. 51.25 ampere. Just check it. 51.25 ampere. Then next, so there are 4 parallel paths. This is a lap-wound machine. So number of poles is equal to number of parallel paths. There are 4 parallel paths. The complete armature current will divide among these paths. So current per parallel path is 205. That is IA divided by number of parallel paths. 205 divided by 4, 51.25. Third is EMF generator. E is equal to V plus IARA. That is, P is terminal voltage, that is 250 volts, plus IA is equal to 205 into RA, armature resistance 0.05. 250 plus 205 into 0.05, that is 260.25. That is the internal voltage or EMF generated. The next is power developed. Power developed is equal to E into IA. That is generated voltage into armature current. That is 260.25 into 205. That is 53.35 kilowatt. 53.35 kilowatt. Next is field copper loss. Field copper loss is voltage across the field into field current. That is, voltage across the field winding is 250 volt. Current is 5 ampere. So field copper loss is equal to 250 into 5. Field copper loss 250 into 5. That is 1250 watts. Then armature copper loss IA square into RA. IA is 205, RA is 0.05. So armature copper loss is 2101.25. You can counter check. You can find out the total power by adding output. Output is equal to 200 into 250. That also I'll write down here. Output is equal to 200 into 250. So it is 50 kilowatt. So output plus field copper loss plus armature copper loss. That is 50 kilowatt plus 1250 watt plus 2101.25 watt. It should be equal to 53.35 kilowatts. So the generated power developed is the sum of output plus field copper loss plus armature copper loss. Next, an 8-pole DC shunt generator has 500 armature conductors and a useful flux per pole of 0.065 L. What is the generated EMF if the machine is lap connected and runs at 1000 RPM? Find the speed at which the machine is to be driven to produce the same EMF if it is wave. So number of poles 8, armature conductors 500, flux per pole 0.065. So in the first case, we have to find the generated EMF if the machine is lap connected and runs at 1000 RPM. The machine is lap connected, then A is equal to 8, and in this case the speed is 1000 RPM. So substituting the induced EMF is equal to 5ZNP by 60. 5ZNP divided by 60. A is 8 and the speed is 1000. Speed is 1000. A is 8. So 541.66 volts. That is the induced EMF. Now the second part of the question is find the speed at which the machine is to be driven to produce the same EMF if it is wave on. So if the machine is wave on, the number of parallel paths is equal to 2. Now we want to produce the same EMF. That means EMF induced should be equal to 541.66. To produce that, what is the speed at which the machine is to be driven? So 541.66 is equal to 5Z N. This is to be found out. P is 8 divided by 60. A is 2 because it is wave on machine. So solving N is equal to 250 RPM. So that's all for today's session. Thank you very much for attending this session. If you feel that the session is useful, please share the video among your friends. Subscribe for the channel and press the bell icon for notifications.